All right, so good afternoon. We discussed the possibility of changing the midterm exam to 16th of March. And based on some exchange with the students in the class, so today we have 30 students on site. So for those of you who are not here and watching this video, please just take this message. So the exam will remain on the 14th of March because we failed to reach a consensus. Okay, so the exam will remain as planned. This is what this is the same time I announced in lecture 1, lecture 13, lecture 14, lecture 15, and today. Okay, so there's no change with regard to the midterm exam. Okay, so it will still be on 14, and this is the coverage. So I'm sorry for I've tried. So again, sorry. All right, so let's start the lecture. It's already late, and thank you for coming. So those of you who contributed to this discussion, thank you. I hope you stay. And today we really have record-breaking number of students. All right, so okay, so next Monday we have this exam, and again, I also want you to. I understand this is never an easy way to please everybody, but please bear in mind that I also announced this. I have designed a rather good insurance policy for you, which means I think I'm the only course which allows 2 options, and the 2 options are so friendly that you, in the end, we are going to calculate your scores based on both options, and we are going to only choose the best score. Okay, best score from the 2 options. If you don't remember what these options are, please go back and watch the video and check the email I sent a while ago. All right, so right, this is enough. Okay, so what did we cover last time? This is the material we talked about. So this is really the recap. This is from last lecture. We started talking about statistical mechanics from last Monday, and we come up with 2 postulates. I hope today, maybe it's not likely given that we already missed some time. There's another important postulate that is really the heart of statistical mechanics, and that I will call it postulate 3. And you are going to see it soon. If it's not today, you will see it on Wednesday next week. Okay, after the midterm. So what did we try to do last time? We started by tossing coins, right? We look at how to play with coins, and that is really the spirit of statistical mechanics. This is something you know very well in schools, and you know how to write out all possibilities for a small system. And we really went through this, right? So what we did was we did a little bit of simple calculation, really, some optimization problem, and we will be able to show that if you have coins, if you talk about the most probable macro state, you find that if you have a large number of coins, it's very intuitive that you get half of them to be head, half of them to be tail, assuming all these coins are distinguishable and even, right? So you put 100 coins in the box, you check, and you count how many of them are head, how many of them are tail, and the most likely scenario is you get something which is half and half. And I also show you how to show that. Okay, we actually went through the proof. Then, but coin is a good problem, but is too simple. We want to look at something a little bit more complicated. Again, this is from last time. This is a slightly more complicated problem. All right, so we are going to talk about this today. So it's important to pay attention on some terminologies. The idea is this: if I have m particles, but I have more than 2 energy levels, you can think of the coin problem as the coin occupying 2 energy levels. One we call head, one we call tail, and there's no way to assign which one is higher, which one is lower. But if I really want to come up with the energy levels, and if I assume they are more than 2, this is the picture. This is the cartoon picture I have. So for each particle, the particle, for each distinguishable particle, I will be able to occupy one of the levels. All right. So if I have n particles, you can imagine I will have n cartoons like this. So now you see 3 potential wells. If I have n, I will have to consider all n of them, and this is really something we are heading to. Okay, so we also assume the atoms will be localized on the lattice, and there is a way for us to distinguish different particles. So I use atom. Maybe we should just use the language of particles. Okay, so if I use the particles localized on the lattice, I will be able to address them. Okay, so everything written in green color is the general case. I'm going to look at the problem subject to the constraint of constant internal energy and constant total particle number. But again, to look at, for us to appreciate this problem, I would like to have the possibility of writing everything down. And that is why I decide to give a simple scenario. As we say, I choose a small system with only 3 particles, and those are written in red. Okay, I set n to be 3, I set u to be 3 epsilon. So I demand the total energy of my 3 particle system cannot be more than 3 epsilon. And then I ask you, what is the way to distribute these particles? All right, so all these, you can see all these energy levels, they have the energies written here. This is my choice. I can we can come up with other combination. Right? You learn quantum mechanics. I just saw from your chat that you take 3022. Very nice. So you know how to solve all this problem. You can easily imagine more complicated situation. Okay, so this is a toy model for us to make some progress. Right. So what kind of progress can we make? So the first thing I asked you last time was to write out a list of all microstates. Okay, so let's try this. All right, I have this same cartoon picture again. Let's see if I can copy and get another one here. All right, so here, I'm not gonna write all for you. So, but I just want you to really appreciate what I meant by this. So remember, this is the case when I have n equals 3 and my internal energy is set by me. Okay, I set it to 3 epsilon. It's me. I decided to do this. Okay, one of the microstates, for example, can be this. We already wrote this one, I believe. But let me write this down because we are going to need it. All right, so I have 3 particles. I just drew 3 dots. And if you sum up all the energy, internal energy, you will see they sum to 3 epsilon. Okay. Another possibility is this. This is, for example, this one, and this one. So all of them will sum to 3 epsilon plus the one we have earlier. I hope it's a different one. Yeah, it's a different one. Okay, so I already gave you 3 microstates, and your task last time was to really write out a list of all of them. This is a small system. You must be able to do that. Okay, so this is one particular microstate, and this is another one, another microstate. Okay, so now, what are the observations I want to make? Okay, the observations I want to make are now I will define for you. This is what I call the macro state. Suppose I have a way to open my box and check the situation of all these particles. Then I want to ask, what is the let me define the. I also call it this distribution. It will become clear why I call this distribution. So I begin to introduce this term. For this system, you don't really have much choice, right? So I will, for example, I will label the microstate 1, 2, and 3. Okay, so 1. Let me check my. Sorry, it better be consistent with the note. So I want one particle will get all the energy. And then okay, so this is one. This is consistent with the note. One particle get all the energy, and the others will have no energy left. Okay, so the other will get 0. Okay, then I can also have the scenario of one particle. I don't really care which one. So this is the point. So one particle get 2, and then one particle gets 1 epsilon, and no more energy left, and the other one will be 0. Get 0. Okay. And the only other possibility will be all 3 particles will get epsilon. Okay. Or 3, sorry, 3 or 3 get epsilon each. Okay, so this is small system is easy to write, right? So I can list out all the possibilities, and that's it. And the question then is, what is the thermodynamic probability or frequency? What is the frequency for this case? So I believe you have done all the writing. So for example, this one, or this ultimately relates to what kind of distribution is most likely to be observed once you open up this box with 3 particles inside. Okay, so right now, again, small system, you can write everything down, but you might not be able to appreciate this yet. Let's quickly finish this. So for distribution 1 is actually fairly simple. Actually, distribution 3 is the simplest, right? 3 particles get epsilon each. This is a bit like having n coins and all of them to be had. What is the frequency for this unnormalized frequency? Right? If you want all the coins, all n coins to be tail, or all n coins to be head, you know that is a very rare occurrence. Okay, and here it turns out that for this case, you have a frequency of 1. Okay, so all of them will occupy here, and you don't care which one, right? But this is only one possible microstate contributing to macrostate 3. Okay, and then for the case 1, this is also easy, right? So you have let's say this is the particle A gets 3 epsilon, then particle B will get 0, particle C will get 0. So this is ABC. Okay, this is the energy of the ABC. Okay, and I have three position for this three epsilon, so I can have this and this. Okay, so the frequency is 3. And this one, I don't want to do it, but the frequency is 6. All right, so from here, we know the most probable distribution is distribution 2 for this simple case. Okay, so from here, this is the most probable. Most probable. Okay, simple. All right, so now this is one way to look at this problem. Now, be careful. I want to do it a little bit differently. So this is the table. You can find the notes. It's the same thing. Right? So this is the case of distinguishable particle. Particles. But it's not a random case. This is the one with n equals 3. U is 3 epsilon, and volume is fixed. Okay. Now, to make progress, I want to introduce a representation. I'm going to call this the occupation number representation. So I will write it down, occupation number representation. Okay. Now, I'm going to give a list. This is the list I need. For me to do the calculation, like what I did last time, optimizing the log of omega. I need to be able to write down the mathematics. So that's why I need this representation. So remember, I'm going to define nj. Now this is a number, okay? So nj is the number of particles having energy epsilon j. Okay, and what is this epsilon j? You should this is my epsilon j, right? Epsilon j is j times epsilon, right? So E naught will be here. Okay, so in this case, I ask how many particles in total are occupying the lowest energy level. Okay, so this is my definition. All right. Okay, so now I want your contribution. Go to the chat and send me the private message and tell me what is this. N0, N1. I want a list, right? This is a list of number separated by comma. Okay, and this goes on forever. But we might not need them for this case because we don't have enough energy. Okay, so I want this list for distribution. Let's choose. Okay, I want distribution 3. What is this list? Okay, so using your chat, just give me this number separated by comma, starting from N0 for distribution 3. Okay, only one answer. More? And this is always a fun exercise. Unfortunately, you have your name here. So I don't want to copy. Okay, every year when I ask this, I get all kind of answer and it's predictable. I get, so the answer given by you are this. I get 1, I get 111. Okay, so this is the answer, possible answer. Okay, and then I get 300. Dot. Okay, and then I also get, let me see, 111, and I get 0100. Okay, some students begin to change their mind, and then I get this one, 0300. Right, so these are all the possibilities. Sometimes I get more, but this year I get this combination. Okay, fun exercise. Okay, one more chance. 1, 2, 3, 4. Which one is correct? 1, 2, 3, 4. Which one is the correct one? You have a chance to change the answer now. Okay. So, sorry, I don't want to. There are students who got it right first and then change it to the wrong answer. Okay, look at this. What do I mean by this? Okay, I want for distribution 3, which is this one, right? Right. So I can tell you on this list. Okay, on this list, there's one correct answer. Don't give me the 5th one. Now I see the 5th answer. 2000100. I don't know. Are you making fun of me or? Okay. The correct answer is this. Right? Why? I think I show it. There's this one here. Right? This is in the energy representation. I will have epsilon, 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 which is distribution 3. Right? All 3 particles get epsilon each. Okay, so as I say, in this occupation number case, you should look around and see. Okay, you go around your system and see how many particles are in 0, so none. How many particles are occupying the first excited state? Okay, so there will be N1. So N0 is 0, N1 is 3, and then the rest are 0. Okay. So this is very important. You need to be comfortable with this language. Now, I kind of accept this one because you probably forget which one is the lowest energy. Okay, so now this is for this case. Okay, so I should put a cross too, but I kind of can see why you get 3 in the first coordinate, first entry, but I don't understand why you get 111 and 0100. So you should think about this. All right, so coming back to here, what we want to do is to be able to come up with a machinery to do the counting, right? So what is the thing I want to count? The thing I want to count is the omega k, which is the number of microstates corresponding to a particular macrostate. Okay, so I'm going, remember I use k to label. I use sub k to label. And for the coin, I told you a convenient k I can choose is the number of head. So for the coin, I did this for the coin. Okay, so here I don't have a good way to do this. I will use this number. Okay, I will just do this. All right, so the general case is this. So for omega k, how do we calculate the number of combination? So how many particles do we have? We have m particles. Okay, again, we need numbers. That's why we want these numbers here. number, not energy. I don't want energy anymore. I want the number of particles occupying that particular energy level, just like the number of coins, right? So this has to make sense this way. Okay, so you have altogether n of them, capital N, and then you have n naught particle in the ground state, and you don't care the sequence of that, the order of that, so you have to divide this out to avoid overcounting. And likewise, you have n1 particle in the first excited state, or the j equals 1 state. You have to divide this out. Okay, so for the coin problem, you only have two possibilities, which stops here. But now you have also have others. So in principle, you have to write all of them out. Okay, so you have m sub j and so on. All right, so let's test. So for omega 3, how many particles? I have 3 particles. And how many in n naught? I have 0. And how many do I have in 1? I have 3 epsilon, and then I have 0 again, and then I get 1. Okay. All right. So this is a general case. Let me box this. Let me box this. All right. One more chance. This one, I will ask the same question. What is this n? This string of n for distribution 2? Okay, again, use the chat. For distribution 2, what do I have? Look at this. And I better be able to get 6 later. Some correct answer, some wrong answer again. Okay, so, don't rush. Spend 30 seconds. Look at this. This is the number of particles in the ground state. You want to change your answer? Okay. The answer is this: 1, 1, 1. Then everything else is 0. Okay, check omega. This is omega 2. Check omega 2. So I have 3 particles, and then the rest is just 1. 1 factorial, 1 factorial, 1 factorial, 0 factorial. Okay, so I have 3 factorial, which is 6. So again, this is checked. Okay. If I ask you now for this small system, you cannot really say too much about this. You might not be able to appreciate the outcome. So let's increase the system size. So here we go. This formula I box, I'm going to use it. I'm going to do this optimization for you, just like what I did for the coin. So let's look at one more case, one more example. So that is, again, this is a distinguishable particle. And this time, I have, this is the case with 6 particles. And I increase the energy I offer to the system, right? This is, again, what I offer to the system. And this is a table in the note as well. You are invited to fill in this. Okay, so if you do it correctly, you will get, all this will sum to, the sum of this column will be 462. Now here, I will explain a little bit more. So this is really the same situation as before. And this K is the index I choose to label the microstate. Sorry, a macro state. So this is altogether I will have 11 macro states. Okay, so this is this column here are the possible macro states. Okay, and you can see I use braces now. That is to say, I already choose not to worry about the order, right? Just like before, in this table, my 3 epsilon is on the left, in the middle, and on the right. Now, there's this notation next door means I don't care about the order. I would just have 3 epsilon 0 0. Order doesn't matter. And likewise, in that notation, I will have braces of 2 epsilon 0. Again, I can swap the order. Okay, so that is the meaning of this notation. Otherwise, this is a huge table, and I do not really want you to write this 120 cases, but you should convince yourself that this is indeed the number. Okay, so what can I tell you? What I can tell you is this is the most probable. Distribution. I give you the number, and then the next probable one is here. Okay, the most probable, and then you have the next probable. Okay. So distribution 6, let's say distribution 6. We can this is the same situation as before. Okay, so I don't want you to do this exercise again. Now actually I take it back. So maybe one more chance to really make sure everyone who reply this time will get it right. Okay, so I want you to do 2 things. Don't look at the note. Okay, don't look at the note, but take your calculator if you want. So I want you to write down. Now again, this is the same potential well as before, but now I have 6 of them. I start from 0 epsilon, 2 epsilon. Okay, but I have 6 of them. Okay, so please write down the case for 2. Okay, so write down n node, n1, n2 for k equals 2. Okay, this one. And give me the omega k. Okay, so for k equals 2, again for k equals 2, and verify the case for k equals 6. All right. So I think what about this? We take this chance to take a break, 10 minutes break, and you can think about this problem. All right, so come back at 1:35 and we are going to continue from here. Welcome back. So before the break, I ask you to give me this answer. I've seen a few and they are all correct. And what about the others? Okay, no guessing, no guessing. This one is K2, sorry, K equals 2. I will tell you this one first. This is 30. And 1. So now you already know. Okay, so I have one particle at M5, N sub 5, 1 at N1, okay, and 4 at N0. So I will start with 4, okay, 4 with N0, N sub 0, and 1 with N1, okay, and then nothing. So this is 1, 2, 3, 4, and then 5, I have one particle, okay, and then 0 and so on. Okay, so number 2, if you do omega 2, it will be the total number of particles is 6, and then I just evaluate all this factorial. Okay, so you have 30. Okay, all right, so it's quite good. It's getting there. So a lot of correct answers are coming in. From here, now what is the point of this exercise? The point of this exercise is for you to have some feeling about this number, this most probable distribution. Do you know what this is? Can you get some feeling already about this most probable distribution? Now you can guess. What is this thing here? If I have a large number, I will be able to get it even more accurately for you. Now this is still quite small, n equals 6. So, but you can hopefully appreciate this. I'm going to plot something for you. I'm going to plot n like this. Okay, so I will have n0, and this is the number of particles really. 1, 2, 3, 4. Okay, I just need 3. Okay, how many particles? So if you look at this, how many particles are in the N0 state? So maybe I should write this for you first. So for k equals 6, which is the most probable distribution, this occupation numbers will be I will have 3 in the ground state, and then 1 in epsilon, 1 in 2 epsilon, and 1 in 3 epsilon, and then nothing. Okay, so I'm going to do it this way, and then on the vertical axis I will give you this. Okay, so the way I want to say is how many particles are in epsilon 0, how many in epsilon 1, and so on. And I can see that for epsilon 0, I get 3. So let me put down this number. So this is 3. Okay, and the rest I get 1. I get 1. I get 1. So these are all 1. 1. Okay, 3, 1, 1, 1, and then 0. So here is really 0. Okay, let me ask you again, what is this thing? This is the most probable distribution. What is this distribution? Again, more answers. No? Okay, let me draw something else. It's not quite accurate. Number is too small. So what about I put this envelope here? Okay, one answer only, and it's not correct. Okay, this is actually some kind of exponential factor. So once we do the math correctly, you will be able to extract something that goes exponentially. That's to say, if I fix the energy, you see, most particle wants to go to the ground state. Is it surprising? Right? And then as you, now this is the most probable state. And if you want all of them to be in 1, that is not very likely. And the most likely one is this one. And this is what you learned before. This is a Boltzmann factor. This distribution is Boltzmann distribution. Okay, so this is for 6 particles you cannot see, but you can already see some trend. We want a lot of particles in the ground states, and then it decay away as you go up in energy. And how fast does it decay? It depends on how much energy you give to the system. Okay, so we use Boltzmann factor to describe thermal equilibrium. So this factor will have a temperature dependence. That's to say, if I fix the temperature, I can ask myself, what would be the distribution of all these distinguishable particles in my systems? Okay, so that is our goal. I want you to recognize once we get to the destination. So this is why we went through this hustle. All right, so you look at omega k, right? So you look at omega k, and if you sum over all this omega k, what I claim is that you get this, right? It's not what I claim. This is you must expect this. So this is the total number of micro. This is a total number of microstates. Right? This is the number of microstates corresponding to the distribution K or macrostate K. So the idea is this: if I have large N, this is the important claim. All this summation is not relevant anymore. You don't need to sum. The total number of microstates will be the same as the number of microstates for the most probable distribution. Okay, so this is a large N. Okay, let me draw a picture for you. So if you have these are all the K, right? So I would just treat it as continuous. If I have small n, you know the situation will be something like this, right? It would be a very broad distribution. And if you sum up all of them, you get big omega. And now, if you have a large n, this is so sharp that you have a very, sorry. Let me draw it again. So this is a small n situation. It might not even be so symmetric. It will be some kind of very broad distribution. And if you have a large number of particles in the system, you basically have a very sharp peak, very sharp. Right? And then it's practically zero outside compared with the maximum. So therefore, if you sum, what do you mean by sum? You really look at what the area below this peak, and this is basically dominated by this omega max. Okay, so this is for large n. And since all these other term, I will draw it for you. They are very small. They are there. It's not completely zero. But this is only going to add a small correction. You might as well just simplify your life and then drop the summation sign. And this is why we call this omega. This is why for the equilibrium distribution, when you have a large number of particles, the omega max for this distribution is the same as the total number of microstates. Okay, so then we can try to optimize now. So this is the K for most probable. This one distribution. All right, so in this case, I can write omega is omega max. And this corresponds to the most probable distribution. So you should imagine it this way, because later I'm going to take the log again and set the derivative to be 0. So you should think of this exercise like this. We are trying to find the combination of n, little n's, that gives you the equilibrium distribution omega max. Okay, and that is the meaning of this line here. Okay, so this is the rest is just really routine. Okay, so let me write it in a more compact way. I will have a product of n sub j, j. Okay, so the first thing is to take log of omega, and that will be the same as log n factorial, which I don't want to care, because I have a fixed number of particles. I'm going to do the differential, and then I have 1 over product, so that that becomes the sum of the log. Okay, and now let's do the Stirling. So Stirling, I don't care about the first term, as I say, and the second term I will have sum over j. This one is log n factorial. I will have n log n minus n. Okay, so this is here I use Stirling. I need to know what happens if I vary this log omega with respect to one of the nj. So be careful now. The notation can be confusing. So for a particular j, let's say you want to look at how log of big omega changes with respect to n sub 100. Okay, so you want to look at this, and how do you look at this? This reduces to the question of taking the derivative. So you are asking yourself, what is this quantity? N 100. Okay, but I want to use this symbol because that is more efficient. Okay, so I just differentiate. I just look at the first line. The first term is gone, and the second term I will have to differentiate everything inside with respect to nj. So if I keep n sub j constant and differentiate log, I get this, and this is a product, so I use the product rule. I will have log n sub j, and nj I differentiate, I get 1, and finally I get 1 here. Okay, and this is 1, this is minus 1, and they cancel. So the end result is this. So this is for a particular j. I will have this result. Okay, I need this because there is what I need for the next line. So next, this is what I need to do. I need to find the equilibrium distribution. So to find the equilibrium distribution, what do I have to do? I have to set this log to be 0, just like before. Now, strictly speaking, what we should do is to set d omega to be 0. I already explained to you why we use log instead. Okay, or equivalently. Okay, so now really we just work it out. So d log of omega. Now this log of omega can depends on all these n subjects. All right, big N is a constant. The rest, any change in the n subject will change the log omega. And therefore we know how to deal with this. This is a function of many variables. So we will have to look at the derivative. So that would be this partial derivative, sorry, and 1. Okay. Right, the change in log omega depends on the change of n1, n2, n3, n4, n5, and so on. And how do they change depends on this partial derivative. So this is all other nj's must be constant except 1. Actually, I don't. I want a different index. I need to keep j. So this is I. Okay. And next term will be the same. I will have the second term, n2, dn2, and so on. So this is n, all other ni's except the one with n2. Okay, so this is compactly, you take this thermodynamic course, so this should not be a problem for you. Okay, so we learn a lot of function of two variables. This is a function of infinite number of variables. Okay, so this is a partial log of omega n sub j. Okay, now this is why I want ni not the same as j, dnj. Okay, and now you know why I want to evaluate this line here. Right, so this line here allows me to work out this one. Right? So I have this, and now I can plug it into here.